Hi there. Okay, in this video there's not going to be any math, so that's cool. But it's really just intended to help you understand what equipotential is and to help you be able to visualize what I've been calling a hill all this time. Now, you know we have the constant electric field condition and then also the spherical electric field condition. Those are going to have certain potentials mapped out for each one. So I want you to visualize in the constant electric field condition, E field or electric field is always truly the slope of the potential. So in other words, if you consider potential to be like a hill or a height or a cliff or something like that, the electric field describes the steepness of the drop. And you can imagine that for this electric field, that the high point of potential is at point A and the low point of potential is at point B, in the same way that the high point of gravitational potential is at point A and lowest is at point B. If you were to place a charge at point A, it would slide down the E field in the same way that a mass would slide down from point A to point B. The only difference, don't forget, in this analog is that there is no negative mass to slide up a hill, whereas on the case of the E field, there is a negative charge to slide up the hill. So if we were to graph the potential, it would look like this, where we can see a point of high potential at point A and low potential at point B. If I were to move over like this, let's say to about 2/3 of the way from A to B, then that would correspond to moving the graph downward like so, so that the 0 point on the potential would now be located right here instead of right here. And the entire thing shifts with it, which represents the fact that electric potential is a relative quantity. If we moved everything back, then they would be like so. Okay, so it's actually a little bit straightforward in the constant electric field condition. It's a little bit harder to visualize for point charges because we really cannot reduce it to a two-dimensional figure. Hard to picture 3 dimensions in 2 dimensions. So, okay, this time let's take a look at a positive charge. Positive point charge would look like this. If we were to graph our potential in this case using the equation that we know, which is that the potential at any point with respect to an infinite distance away is the Coulomb constant Q over R, then the graph would look something like this. Here, where the charge is, there would be some potential. Now, it would never truly touch 0, because you'd have to get infinitely far away to do so, right? This is a little trickier, because although it's pretty simple in the case of 1 point charge, it looks a little bit more complicated when you put 2 point charges down. Now, these 2 point charges are not actually on the graph. We're going to be graphing the potential due to one charge and due to the other, and we're basically just observing what happens if we move from left to right across these charges. So, or R if you prefer to look at it as R. Alright, for our charge that's on the left, let's go ahead and choose a color. We'll choose something a little bit yellow. And we're going to look at the potential due to this charge, which should look something like this. Whoops. As we saw before. I never can quite get this right. Okay. Now, assuming that this is going to be an identical charge over here, we should have a similar figure for this one. Now, the sum, unlike vectors, the sum of potentials is pretty much just the sum of potentials, so you don't have to worry about using Pythagorean theorems and components or any of that. The beauty of potential hills and potential mapping is that you basically just say what's the influence due to charge 1, what's the influence due to charge 2, add them together, and you have the potential surrounding your entire configuration. So what we're going to do here is just basically take a look at each point. So let's take a look at this point right here and determine what the total potential is there. It's going to be this value plus that value. Both of them are positive, so they'll add constructively, and that gives us a total value about there, right? So then we'll keep doing that everywhere. So we'll right on the edge here, should be something like this, a little higher on this side. Go right here, something like that, same over here. As a matter of fact, we can use symmetry here. Well, we would be able to if I had done it right. That's a little better. Okay. There we go. It's getting there. Okay. And then this point over here. So gradually this yellow is going to have less and less influence on this curve. It's really going to have more of an influence right here, right? So once we stack all this together, then you can see that the sum potential is going to look something like a double mountain, like this. So this would be the potential in this situation. Now, yeah, sure, okay, why though? What's the point of it? Well, remember, we're talking about hills, right? A potential is just a hill. If you took a ball and rolled it on this blue hill here, then what would it do? Well, it would roll to the other side and then come back again, and then come back again, and then come back again. Now, what if you took a positive charge and placed it in between these two? Well, it would go to here, to a stopping point where it would be repelled by this one, and then be pushed back to this one, and then go back and forth and back and forth. This potential hill is a really useful tool for visualizing what would happen. Well, what if it managed to get around this charge? Well, if it managed to get around this charge, then it would take off, right? In the same way that a ball on this hill would manage to, if it managed to get around, it would just take off, right? So essentially what we're looking at here is mountains and valleys. With a positive charge and a negative charge of equal value, we have ourselves a dipole. So we get some interesting effects that occur here. If we were to add up the total potential, we would get something that looks a little bit more like this. So the influence here would be this amount minus that amount. And we would do that everywhere. So the influence becomes greater and greater until we end up at a point where there is just as much up as there is down, meaning that the total potential becomes 0 at that point, and then crosses over the line. So we're going to end up with a potential in sum total that looks something a little bit more like this: a mountain and a valley. Now again, imagine what a ball would do. If you place the ball right here, then you can imagine that it would just roll straight downhill and then collide into the valley, right? If it managed to miss the valley right here, then it would swoop around and continue going, right? In the same way that a charge, if it were a positive charge, then would go around this charge and be slingshot, like this, right? In three-dimensional space, that is. Not having any, not being on this graph, just being a charge that's flying through space, right? And so this actually gives you a hint about what's going to happen to these charges, and really kind of gives you a sense of what the potential looks like visually in the surrounding space. You can also think about E field in the vicinity. So here, right in the middle, we saw that the E field here is definitely not 0. We've seen that previously, because the slope is actually quite concentrated at this point, right? The slope is pretty severe everywhere in here, right? Right in between. But conversely, on the previous charge that we had, the positive charge and another positive charge, the midpoint in there was an electric field equal to 0, while the potential was certainly not. It was actually quite high, right? Not as high as the charges themselves, but on the double mountain, it was still up there. So it's important to keep these two distinct. Remember, potential is the hill. The electric field that we've studied is the steepness of the hill.